Hi there, and welcome to this video brought to you by BC Housing's Mobilizing Building Adaptation and Resilience program. This video is part of a province-wide training series hosted by BC Housing, designed to prepare builders, designers, building officials, and others to meet the increasing need for climate resilient design. In this presentation, I'll be providing an overview of the BC Energy Step Code Design Guide Supplement on overheating and air quality. Let's get started. By way of introduction, I'm Lisa Westerhoff. I'm a principal at Integral Group, and I lead our policy and planning team out of the Vancouver office, where we work with provinces and municipalities and organizations like BC Housing to try to shift the market in creating or helping to create requirements, standards, guidelines, and other materials to help design and construct a more resilient building sector. Here talking today on behalf of the MBAR program, whose aim is to really build our understanding of how we can increase the number of resilient buildings across the province of British Columbia. MBAR is a multi-year, multi-stakeholder project designed to grow our knowledge of how to design, renovate, and manage for resilience, and to ultimately share that knowledge across the building industry in BC. And I'll be talking today about one of the resources that the MBAR program has released, which is the BC Energy Step Code Design Guide Supplement. And this supplement outlines the strategies that designers can consider when they're looking to not only improve a building's energy efficiency, as required by the BC Energy Step Code, but also to mitigate the growing risk of overheating and air quality issues. The reason why we need this kind of a design guide supplement is because we know across British Columbia, average annual temperatures and temperature extremes are going up, and that generally buildings that are constructed today using climate parameters based in the current building code aren't going to be suitable for tomorrow's climate. And the reason for that is because we're still using climate data from the past to make decisions about buildings that are going to be around for really years to come when our climate will look very different. And we know that this is actually also going to create impacts to occupant thermal comfort, or in other words, the satisfaction that occupants or residents will have with the temperature in a particular space. For example, an occupant may not be able to use the building space as they were designed to. It may become too warm to sleep in a bedroom at night. You may actually also even leave the building altogether if it becomes uncomfortably hot. And overall, it interrupts an occupant's ability to live and work normally. We also know that overheating risk is something that we need to consider as well. And this is when spaces become too warm for their occupants and that prolonged and dangerously high temperatures can ensue, creating health risks, especially for those people and populations that are more vulnerable. Warmer temperatures and drier summers are also going to bring with them an increased risk of wildfires. And the extreme wildfires of the last few years, 2017, 2018, 2020, have all showed us a little bit of what we can expect more of in the future. We know even if you're not located right next to one of these fires, they can be accompanied by heavy smoke that will carry with it a range of negative health impacts, again, especially for vulnerable populations. So this design guide supplement was really created to cover a range of these different topics, to provide designers and others interested in resilient buildings, to help them understand what the impacts of a warming climate may be on buildings. A little bit of understanding of how we can design for the future instead of designing using past climate data. And then finally, a set of strategies that can be used to help reduce energy demand or improve energy efficiency, but also minimize the risk of overheating and indoor air quality issues. And it's those different strategies, passive strategies, active mechanical strategies, considering air quality and looking at refuge areas, which are the things that I'm going to be talking to you about in the rest of this video. And what's important to keep in mind as we go through is that there's really a need to balance the various risks and strategies and trade-offs that you have to make between reducing overheating, ensuring good air quality, and maintaining good energy efficiency. And really to keep these in mind for your project specifically. For example, we know that shading can lower the risk of overheating in the summer. But if you don't implement it carefully, it can actually lower your passive solar gains in the winter, which you want to reduce your overall thermal energy demand intensity. And the same actually goes for low solar heat gain glazing as well. Operable windows are a measure that you can use to reduce your risk of overheating. It's a passive strategy that uses very little energy or no energy at all. But it also can increase the risk of air quality issues since you're opening the window up to the outside and to whatever smoke or other sources of air pollution may be out there. Adding mechanical cooling can overcome that issue by allowing you to cool spaces without having to open the window, but then you're increasing your overall energy demand. So really trying to think about all these things as they work together is really important, again, for whatever specific project and set of circumstances you're designing in. So that being said, these are all good sort of good practice or best practice strategies that I'll go through, but do keep in mind that they may look a little bit different on the project that you're working on, and you need to carefully consider each one to make sure that you're trying to maximize the achievement of all the different goals that you have. So the design guide supplement starts with passive strategies. It outlines the passive strategies necessary to reduce both your thermal energy demand, but also improve your thermal comfort inside. 3 of these strategies that it goes into in some detail include ensuring a continuous air barrier around your envelope, maximizing your R values wherever possible, and minimizing thermal bridging. All of these strategies can help to keep warm air inside of a building in the wintertime, but they can also help to keep cooler inside a building when it's considered carefully alongside some of the other strategies that we'll review. The second passive design strategy the guide supplement outlines is to identify an appropriate window-to-wall ratio, or your glazing strategy. Lower window-to-wall ratios can reduce solar gleams in the summer, which is good, and since glazing often has lower insulating properties than opaque assemblies, it can also help to reduce heating loads in the winter. To maximize your control over heat gains, south and north facades typically should have or can have higher window-to-wall ratios than on the east and west facades. Again, this will depend on your particular project and your context that you're working in. The third step, or third sort of set of passive design strategies, is to look at shading and as a way to reduce your passive solar gains in the summer while maximizing them when you want them in the wintertime. Generally speaking, maximizing glazing on the south facade and shading it appropriately is a way to harness those solar gains when you do want them, and is generally a best practice to follow. On the east and west facades, different shading strategies could be used, all of which have different pros and cons. For example, you might want to use a perforated screen, which offers a shading element and also a decorative element, but it can also reduce those incoming gains in the winter, so you have to think about where you're going to place that pretty carefully. Semi-transparent shades can also be quite effective, but they often do require maintenance and can be susceptible to occupant disruption or interaction. So again, a consideration to take into account. Horizontal overhangs often work best on a southern facade since they block that high southern sun in the summertime. Balconies are also a good strategy here. And vertical shades can pretty much work on any facade, but they also may reduce passive heating in the winter. So again, careful placement and a careful study is required for each individual project. The fourth sort of passive strategy or set of passive strategies is to explore natural ventilation to help achieve thermal comfort. This basically means just increasing the flow of outdoor air into a space through openings in the building envelope, such as windows. Getting that air movement can really help to improve thermal comfort without the need to actually cool your space with mechanical cooling or through a ventilation system. And while you can get some natural ventilation on a window or on a single facade, air movement is much better, much greatly enhanced when you use cross ventilation strategies. So putting a window or an opening at opposite or different sides of a unit or a space. This can really help achieve thermal comfort for your occupants for significant portions of the year. That said, we know that with increasing temperatures, these passive strategies aren't necessarily going to be enough in some of the warmer months of the year as those temperatures increase, or in those extreme temperature events. And this is when combining passive with more active strategies really comes into play. In other words, taking a more hybrid approach. These kind of hybrid systems are really ideal for increasing the overall airflow and improving thermal comfort in a cost-effective and an energy-efficient way, and can often be sufficient in place of a full mechanical cooling system. Some examples of hybrid cooling systems include using a bypass in your heat recovery ventilation unit to help ensure that cooler air brought in into a building from the outside avoids absorbing any heat from the warm air being exhausted, helping to keep your indoor temperatures lower. So this strategy is effective when your indoor temperature buildings are higher than your outdoor building temperatures. You also may want to consider driving air movement with your exhaust fans. When outdoor temperatures are cooler than indoor temperatures, an open window at one end of a space and an active exhaust fan at the other can help drive air movement more than with just passive means alone. For those systems using a centralized HRV, you may adapt those to cool or temper ventilation air by adding a cooling coil. So a few different strategies to consider. Of course, peak summer conditions today are already starting to make certain passive or even hybrid strategies ineffective, which means that in a lot of situations, mechanical cooling really needs to be considered. Of course, there's lots of different ways to add mechanical cooling, but we recommend that you give consideration to your low carbon energy systems to reduce your greenhouse gas emissions, but also, of course, giving consideration to high performance technologies like heat pumps that will lower your total energy use intensity. Consideration should also be given to how cooling is provided. For example, zoning your system based on external gains is a good way to maintain thermal comfort and also reduce your energy use intensity. In some cases, you may have a project where you don't feel that mechanical cooling is really necessary today, or you may not have, the financial means of adding it. In these cases, considering rough-ins for adding mechanical cooling systems at a later date is a strategy that could be considered. In these cases, you may need to plan your future routes for running your future refrigeration or chilled water lines. You may need to specify equipment with the space to add cooling coils, and you may need to size your airflow rates to meet future cooling loads. In all cases, you should also think about the provision of future electrical capacity to accommodate those future cooling systems, both building-wide and in specific spaces. Overall, what we try to illustrate with the guide is that you really need to carefully consider what combination of passive and active strategies is going to work best for your particular project. By mixing your modes, you're giving more flexibility to the way that thermal comfort can be achieved. When outdoor temperatures are low, passive strategies in combination with some of those lighter touch mechanical cooling or hybrid systems will likely be enough, keeping both your indoor temperatures low and maintaining a low energy use intensity. During those peak seasonal temperatures, that's when maybe switching to a full mechanical strategy might actually work best. As we mentioned before, mechanical systems also offer the ability to close up all your windows, sort of seal up all your building when your outdoor air conditions become poor, such as in the case of an outdoor wildfire event. Of course, it's important to identify that there are many different sources of air contaminants, including indoor sources of contaminants, that you need to minimize in your design and in your operations. But when outdoor air sources of pollutants from traffic, construction, or wildfire smoke increases, this is when it starts to really threaten air quality in a space. So it's always important to identify the likely sources of air contaminants when you're designing your system, including the likelihood that hazards like regional forest fire events may actually increase into the future. Current air quality standards for British Columbia are, of course, defined in the BC Building Code and in ASHRAE 62.1, both of which set minimum ventilation requirements to maintain carbon dioxide, particulate matter, and other contaminant concentrations below certain thresholds. However, if you're interested in pursuing higher air quality standards, you can find examples in the LEED and the WELL building standard, both of which identify thresholds for various pollutants, but also that require verification to demonstrate compliance. Generally speaking, in any case, filtering ventilation air we know will be increasingly important as wildfire smoke events are likely to increase in British Columbia. So project designers should identify the number and the intensity of local sources of air pollutants to determine the level of filtration that should be used in their project. MERV 13 is now recommended as the minimum level of air filtration to ensure good air quality during those air events or air quality events, but ideally you could go even higher, and may also want to consider activated carbon systems for areas where external pollutants or volatile organic compounds are higher. Since high performance filtration may not be required all year round, it is possible to design to allow for space in your air handling units to allow higher performing filters during bad air quality events. This of course requires some consideration of the maintenance and the operations of the building, but it can be a good kind of low cost and sort of high energy efficiency way to add increased air quality to your building. Of course, also standard good practices also apply. You want to make sure you're locating your air intakes as far away from pollution sources as possible and using demand control ventilation to control pollutant concentrations in a space is a good idea to help reduce energy use by supplying only the amount of outdoor air that is required at any given time. Finally, the design guide design guide supplement looks at circumstances under which resources may be constrained or other situations in which the full suite of recommended measures that I've presented here aren't really feasible to be introduced at an individual unit level. In these cases, designers may want to consider designing one or more common areas inside of a building as a refuge area, and that can help actually build overall resilience to both indoor air quality issues and heat events. Basically, what these do is provides occupants or building community members with a place of respite in the event that their own units become uncomfortable or unsafe. These kinds of refuge spaces can be included alongside of or in place of some of the strategies that I've just discussed already. In summary, the Design Guide Supplement is a great resource to understand how you can achieve not only energy efficiency outcomes in your new building design, but also to help plan for the future and reduce the risk of overheating and air quality issues. It's important to always plan for the future and make sure that you're using future climate files when looking at the performance of your building. Start with passive cooling and passive design strategies wherever possible to help keep your energy use low. Use shading to block those solar heat gains, and then start to look at how you can couple passive cooling strategies with hybrid or mechanical systems, including looking at roughing in for the future where you may not want to actually add them in today. Looking at including enhanced air filtration for both day-to-day and for those extremely poor air quality events is important to keep the safety and health of your occupants throughout the life of the building. And again, if you're not able to look at these strategies on a unit-by-unit scale, looking at providing a refuge with cool, clean air is a great strategy to consider as well. That concludes this video. We'd like to thank the funders that made all of this work possible, including, of course, BC Housing, who led the MBAR program, as well as many of the other contributors that have continuously contributed their knowledge and expertise to these kinds of guides. Interested in looking at more resources or learning more about the MBAR program, you can reach the program at mbar@bchousing.org or just visit bchousing.org/MBAR. Thank you.